Lab 4 Oscillations. Intro. The purpose of the lab is to simulate a mass spring oscillation using VPython. We model how the energy changes over time as the mass moves. The goal is to compare the simulation to the expected physical behavior of the ideal oscillation. This one is the uh, physical behavior, and this one would be the ideal. What's what? The system is a oscillating mass attached to a spring. Mass could be the soccer ball attached to this spring, and the surroundings would be gravity of the earth, and the anchor, a spring anchor, which would be attached to the opposite end of the spring, keeping it still. The forces involved are the spring force and the gravitational force. How do we model it? Use the net force to update velocity, and the initial position come from the tracker used on the observed data. So the formula for V final is V initial plus F net divided by times delta T, and using the average V average, update the position, go R but you get R final, you get R initial plus V average times delta T, and the spring force is negative K and L minus L naught times L hat. What did I do? Define the mass, spring constant, and equilibrium position. Calculate forces each of the loop of the code. Update position and velocity, and compute the energies below each step, or the energies below in each step. And last, apply a graph of time versus energy, and these are the formulas for the forces, not forces, energies. These two, energies. This is gravitational potential energy and spring potential energy, and this is kinetic energy. And this is the graph, which you can see energy. Constant. Total energy is moving constantly for the most part, and this is the code. And then discussion. Total energy stays nearly constant. Energy is conserved. Kinetic and spring energy trade off periodically. Gravitational energy changes if the vertical motion is included, and small numerical drifts may appear due to the time step size, since it is so detailed. The simulation successfully models oscillatory motion, energy transformations, and matched the theoretical predictions. VPython allowed the visualization of how forces and energies evolve over time, as Tx and Ty of the peaks are pretty close, differing only slightly due to tracking noise and small misalignment between motion and coordinate axis. So overall, they support consistent oscillation.